Hello everyone, this is Srijit and welcome to the subject MCAC 35 Advanced Database Systems. Today we will start a new module, the second module, which is divided into two parts, data analysis and mining, then information retrieval. First, let's see the data analysis and mining part. In this section, we will discuss about decision support systems, data analysis and OLAP, what are data warehousing and data mining, then classification and association rules, finally clustering. Lately, businesses have begun to exploit the ever-expanding data online to make better decisions about their activities, such as what items to stock and how best to target customers to increase sales. There are two aspects to exploiting such data. The first aspect is to gather data from multiple sources into a central repository called a data warehouse. Issues involved in warehousing include techniques for dealing with dirty data, that is, data with some errors, and with techniques for efficient storage and indexing of large volumes of data. The second aspect is to analyze the gathered data to find information or knowledge that can be the basis for business decisions. Some kinds of data analysis can be done by using SQL constructs for online analytical processing and by using tools and graphical interfaces for OLAP. Another approach to getting knowledge from data is to use data mining, which aims at detecting various types of patterns in large volumes of data. Data mining supplements various types of statistical techniques with similar goals. Now let's see what are decision support systems. We can divide database applications into two categories. First one is the transaction processing system and then the decision support systems. Transaction processing systems, as we learned before, are systems that record information about transactions, such as product sales information for companies or post registration and grade information for universities. On the other hand, decision support systems aim to get high-level information out of the detailed information stored in transaction processing systems and use the high-level information to make a variety of decisions. For example, a company database often contains enormous quantities of information about customers and transactions. Transaction information for a retailer may include the name or identifiers such as credit card numbers of the customer, item purchased, the price paid, and the dates on which the purchases were made, etc. Information about items purchased may include the name of the item, the manufacturer, the model number, the color, and the size. Customer information may include credit history, annual income, residence, age, and even educational background. Such large databases can be treasure troves of information for making business decisions, such as what items to store and what discounts to offer. For instance, a retailer company may notice a sudden spurt in purchases of flannel shirt in the Pacific Northwest, may realize that there is a trend and may start stocking a larger number of such shirts in shops in that area. The storage and retrieval of data for decision support raises several issues. We can write many decision support queries in SQL, but some of them either cannot be expressed in SQL or cannot be expressed easily in SQL. Several SQL extensions have therefore been proposed to make data analysis easier, so we can use SQL extensions for data analysis and techniques for online analytical processing or OLAP. Database query languages are not suited to the performance of detailed statistical analysis of data. There are several packages such as SAS and S++ that help in statistical analysis. Such packages have been interfered with the databases to allow large volumes of data to be stored in the database and retrieved efficiently for analysis. Large companies have diverse sources of data that they need to use for making business decisions. The sources may store the data under different schemas. To execute queries efficiently on such diverse data, companies have built data warehouses. Data warehouses gather data from multiple sources under a unified schema at a single site. Thus, they provide the user a single uniform interface to data. The knowledge discovery technique attempts to discover automatically statistical rules and patterns from data. The field of data mining combines knowledge discovery techniques invented by artificial intelligence researchers and statistical analysts with efficient implementation techniques that enable them to be used on extremely large databases. We can see that the area of decision support can broadly cover all the above areas, although some people use the term in a narrower sense that excludes statistical analysis and data mining. Now let's see what data warehousing is. Data sources often store only current data, not historical data. When it comes to corporate decision making, it requires a unified view of all organizational data, including historical data. A data warehouse is a repository or an archive of information gathered from multiple sources, stored under a unified schema at a single site. Once gathered, the data are stored for a long time, permitting access to historical data. Thus, data warehouses provide the user a single consolidated interface to data, making decision support queries easier to write. Moreover, by accessing information for decision support from a data warehouse, the decision maker ensures that online transaction processing systems are not affected by the decision support workload. Now let's see the components of data warehouse. Figure shows the architecture of a typical data warehouse and illustrates the gathering of data, the storage of data, and the querying and data analysis support. Here we have multiple data sources from which the data loaders gather data to the DBMS. Loaders and DBMS forms the data warehouse. Then we have a number of query and analysis tools that work on the data gathered at the data warehouse. Let's see the issues to be addressed in building a warehouse. The first one, when and how to gather data. In a source-driven architecture for gathering data, the data sources transmit new information either continuously, as a transaction processing takes place, or periodically, like nightly or fortnightly. In a destination-driven architecture, the data warehouse periodically sends requests for new data to the resources. Unless updates at the sources are replicated at the warehouse by two-phase commit, the warehouse will never be quite up to date with the sources. Two-phase commit is usually far too expensive to be an option, so data warehouses typically have slightly out-of-date data that, however, is usually not a problem for decision support systems. Then, what schema to use? Data sources that have been constructed independently are likely to have different schemas. In fact, they may even use different data models. Part of the task of the warehouse is to perform schema integration and to convert data to the integrated schema before they are stored. As a result, the data stored in the warehouse are not just a copy of the data at the sources. Instead, they can be more of an materialized view of the data at the sources. Next is the data transformation and cleansing. The task of correcting and pre-processing data is called data cleansing. Data sources often deliver data with numerous minor inconsistencies which can be corrected. For example, names are often misspelled and addresses may have street, area, or city names misspelled or postal code entered incorrectly. These can be corrected to a reasonable extent by consulting a database of street names and postal codes in each city. The approximate matching of data required for this task is referred to as a fuzzy lookup. Then comes the merge-purge operation. Address lists collected from multiple sources may have duplicates that need to be eliminated in a merge-purge operation. This operation is also referred to as deduplication. Records for multiple individuals in a house may be grouped together, so only one mailing is sent to each house. This operation is called householding. Data may be transferred in many ways other than cleansing, such as changing the units of measure or converting the data into a different schema by joining data from multiple source relations. Data warehouses typically have graphical tools to support data transformation. Such tools allow transformation to be specified as boxes, and edges can be created between boxes to indicate the flow of data. Conditional boxes can route data to an appropriate next step in transformation. So how to propagate these updates? Updates on relations at the data sources must be propagated to the data warehouse. If the relation at the data warehouse are exactly the same as those at the data source, the propagation is straightforward. If they are not, the problem of propagating updates is basically the view maintenance problem. So a problem with the materialized views is that they must be kept up to date when the data used in the view definition changes, or the view will become inconsistent with the underlying data and it must be updated. The task of keeping a materialized view up to date with the underlying data is known as view maintenance. So what are materialized views? When a view is defined, normally the database stores only the query defining the view. In contrast, a materialized view is a view whose contents are computed and stored. It can improve system performance as the query computation are not required each time when the view are accessed. Then, next problem is what data to summarize. The raw data generated by a transaction processing system may be too large to store online. However, we can answer many queries by maintaining just summary data obtained by aggregation on a relation, rather than maintaining the entire relation. For example, instead of storing data about every sale of clothing, we can store total sales of clothing by item name and category. Suppose that a relation R has been replaced by a summary relation S, users may still be permitted to post queries as though the relation R were available online. If the query requires only summary data, it may be possible to transform it into an equivalent one using S instead. The different steps involved in getting data into a data warehouse are called extract, transform, and load, or ETL tasks. Extraction refers to getting data from the sources, while load refers to loading the data into the data warehouse. Now let's see warehouse schemas. Data warehouses typically have schemas that are designed for data analysis using tools such as OLAP tools. Thus, the data are usually multidimensional data with the dimension attributes and measure attributes. Tables containing multidimensional data are called fact tables and are usually very large. A table recording sales information for a retail store with one tuple for each item that is sold is a typical example of such fact table. The dimensions of the sales table would include what the item is, usually an item identifier such as that used in barcodes, the date when the item is sold, which location or store, then the item was sold from, which customer bought the item, and so on. The measure attributes may include the number of items sold and the price of the items. To minimize storage requirements, dimension attributes are usually short identifiers that are foreign keys into other tables called dimension tables. For instance, a fact table sales would have attributes item ID, store ID, customer ID, and date, and measure attributes number and price. The attribute store ID is a foreign key into a dimension table store, which has other attributes such as store location, that includes city, state, country. The item ID attribute of the sales table would be a foreign key into a dimension table item info, which would contain information such as the name of the item, the category to which the item belongs, and the other item details such as color and size. The customer ID attribute would be a foreign key to a customer table containing attributes such as name and address of the customer. We can also view the data attribute as a foreign key into a date info table giving the month, quarter, and year of each date. The resultant schema appears like what in this figure. Such a schema with a fact table, multiple dimension tables, and foreign keys from the fact table to the dimension table is called a star schema. More complex data warehouse designs may have multiple levels of dimension tables. For instance, the item info table may have an attribute manufacturer ID, that is a foreign key, into another table giving details of the manufacturer. Such schemas are called snowflake schema. And complex data warehouses design may also have more than one fact table Collection of fact tables with the common dimension tables are known as constellation of fact tables. Now let's see what OLAP is. Online Analytical Processing Server or OLAP server is based on the multidimensional data model. It allows managers and analysts to get an insight of the information through fast, consistent, and interactive access of information. So what is multidimensional data model? A multidimensional model views data in the form of a data cube. A data cube enables data to be modeled and viewed in multiple dimensions. It is defined by dimensions and facts. The dimensions are the perspectives or entities concerning with the organization keep records. For example, a shop may create a sales data warehouse to keep records of the store's sales for the dimension time, item, and location. These dimensions allow us to keep track of things, for example, monthly sales of the items and the locations at which the items were sold. Each dimension has a table related to it called a dimensional table, which describes the dimension further. For example, a dimensional table for an item may contain the attributes item name, brand, and type. We have just discussed this in the above topic. Okay. A multidimensional data model is organized around a central theme. For example, sales. This theme is represented by a fact table. The facts are numerical measures. The fact table contains the names of the facts or measures of the related dimensional tables. So consider the data of a shop for items sold per quarter in the city of Delhi. The data is shown in the table. This 2D representation, the sales of Delhi, are shown for the time dimension organized in quarters and the item dimension classified according to the types of the item sold. The fact or measure displayed in rupee sold, or that is in thousands. Now if you want to view the sales data with the third dimension, for example, suppose the data according to time and item as well as the location is considered for the cities Chennai, Kolkata, Mumbai and Delhi. These 3D data are shown in the table. Here the 3D data of the table are represented as a series of 2D tables. Conceptually, it may also be represented by the same data in the form of a 3D data cube as shown in the figure. Here we added location as a third dimension to form the data cube. There exist different types of OLAP servers which provide its own services. Basically, we have four types of OLAP servers: the relational OLAP or OLAP, multidimensional OLAP or MOLAP, hybrid OLAP or HOLAP, and finally we have specialized SQL servers. The relational OLAP. OLAP servers are placed between the relational backend server and client front-end tools. To store and manage warehouse data, OLAP uses relational or extended relational DBMS. OLAP includes the following: the implementation of aggregation navigation system logic, optimization for each DBMS backend, and additional tools and services. OLAP servers are highly scalable and it uses tools to analyze large volumes of data across multiple dimensions, and OLAP tools store and analyze highly volatile and changeable data. Then we have the multidimensional OLAP or MOLAP. MOLAP uses array-based multidimensional storage engines for multidimensional view of data. With the multidimensional data stores, the storage utilization may be low if the data set is sparse. Therefore, many MOLAP servers use two levels of data storage representation to handle dense and sparse data sets. So, the advantages of MOLAP are: MOLAP allows fastest indexing to the pre-computed summarized data, and it helps the users connected to a network who needs to analyze larger, less defined data. It's easier to use, therefore MOLAP is suitable for inexperienced users. There are disadvantages to MOLAP that include they're not capable of containing detailed data, and the storage utilization may be low if the data set is sparse. Let's see the difference between MOLAP and OLAP. See, MOLAP information retrieval is fast, while in OLAP it is comparatively slow. In MOLAP, it uses sparse array to store data sets, while OLAP uses relational table. MOLAP is best suited for inexperienced users since it's very easy to use, and OLAP is usually is suited for experienced users. OLAP maintains a separate database for data cubes, and OLAP may not require space other than available in the data warehouse. And in case of OLAP, DBMS facility is weak, but it is very strong in case of OLAP. Next is the hybrid OLAP. Hybrid OLAP is a combination of both OLAP and MOLAP. It offers higher scalability of OLAP and faster computation of MOLAP. OLAP servers allows to store the large data volumes of detailed information. The aggregation are stored separately in MOLAP store. Then we have specialized SQL servers. Specialized SQL servers provides advanced query language and query processing support for SQL queries over star and snowflake schemas in a read-only environment. Now let's see the OLAP operations. Since OLAP servers are based on multidimensional view of data, we will discuss OLAP operations in multidimensional data. So these are the list of operations under OLAP: roll up, drill down, slice and dice, then pivot or rotate. First, let's see a roll up. A roll up performs aggregation on a data cube in any of the following ways: by climbing up a concept hierarchy for a dimension, or by dimension reduction. The diagram shows how a roll up works. Here, roll-up is performed by climbing up a concept hierarchy for the dimension location. Initially, the concept hierarchy was street, city, province, country. On rolling up, the data is aggregated by ascending the location hierarchy from the level of city to the level of country. The data is grouped into cities rather than countries. When roll-up is performed, one or more dimensions from the data cube are removed. Next, let's see drill down. Drill down is the reverse operation of roll up. It is performed by either of the following ways. First, by stepping down a concept hierarchy or a dimension, or by introducing a new dimension. The following diagram illustrates how drill down works. Here, drill down is performed by stepping down a concept hierarchy for the dimension time. Initially, the concept hierarchy was day, month, quarter, year. On drilling down, the time dimension is descended from the level of quarter to the level of month. When drill down is performed, one or more dimensions from the data cube are added, and it navigates the data from less detailed data to highly detailed data. Next is slice. The slice operation selects one particular dimension from a given cube and provides a new subcube. Consider the following diagram that shows how slice works. Here, slice is performed for the dimension time using this criterion time is equal to quarter 1. It will form a new subcube by selecting one or more dimensions. Next is dice. Dice selects two or more dimensions from a given cube and provides a new subcube. Consider the following diagram that shows the dice operation. The dice operation of the cube based on the following selection criteria involves 3 dimensions. Location is equal to Toronto or Vancouver. Time is equal to quarter 1 or quarter 2. An item, mobile or modem. Finally, we have fifth, that is the pivot operation. The pivot operation is also known as rotation. It rotates the data axis in view in order to provide an alternative presentation of data. Consider the following diagram that shows the pivot operation. Here, we rotate the location and item axis to get an alternative view of the same data. Thank you for listening to the class. We will continue with data mining in the next class.